Roadwork and the associated work zones are an integral part of the life cycle of the nation's roadways and are essential to maintaining and upgrading our nation's transportation system. Unfortunately, the accompanying changes in traffic patterns, narrowed lanes, debris, and other construction activities often compound, resulting in reduced capacities and confusion, excessive delays, crashes, injuries, and fatalities for both road users and construction workers. According to the Federal Motor Carrier Safety Administration, also known as FMCSA, while commercial motor vehicles, or CMVs, comprise only about 5% of overall traffic, they contribute to 33% of all fatal crashes at work zones. Through the National Roadway Safety Strategy, the U.S. Department of Transportation is adopting the Safe System approach. One key element of this approach is making vehicles safer for their occupants and all road users. As part of this, FMCSA is collaborating with the Federal Highway Administration, also known as FHWA, the Volpe National Transportation System Center, or VOLPE, and the Maritime Administration, also known as MARAD, to perform multimodal freight research for the safe integration of automated CMVs into the transportation network. As part of these efforts, FMCSA funded research through their Automated CMV Evaluation, or ACE program for short, to develop and demonstrate a proof-of-concept application for the safe operation of self-driving CMVs with mixed traffic in work zones. The concept leverages prior work products developed in FHWA Workzone research for passenger vehicles. The concept was validated and demonstrated in April 2022 at the SunTrax test facility located in Auburndale, Florida. The project demonstrated connected and automated vehicle technology for the interaction of two automated CMVs with work zones in a mixed traffic environment, including an automated passenger vehicle. Building upon existing open-source Karma software through agile software development and testing, the test event provided data, analyses, and results to inform national consensus-based best practices and standards. For this study, a mock work zone was established along the closed test track, mimicking a lane closure on the highway with drums, signs, and construction equipment outlining its configuration. 3 core actions were considered for the safe passage of an automated truck through the work zone. First, the truck acknowledged the work zone geofence information received from the infrastructure at the work zone. The truck then reduced its speed as it approached the work zone. Lastly, the truck adjusted its trajectory to change lanes, considering a restricted lane use regulation. To begin, 2 automated trucks and an automated passenger vehicle traveled on the highway at a normal speed. As the demonstration started, each vehicle wirelessly transmitted identifiers to the roadside infrastructure. The infrastructure then communicated with Karma Cloud, which represents a traffic management center in this scenario. Karma Cloud sent the work zone geofence, reduced speed, and lane use restrictions back to the roadside infrastructure. The infrastructure repeatedly sent the information received from Karma Cloud to the vehicles. Each vehicle wirelessly communicated back to the infrastructure, acknowledging that they received the work zone information. The vehicles proceeded to enter the reduced speed zone. If the trucks did not acknowledge receipt of the work zone geofence information, either because they were unable to process the messages from the infrastructure or because they did not receive those messages, then further action would be taken. First, a warning was registered on Karma Cloud. Second, a visual and auditory warning was sent from the infrastructure to the work zone operator to warn the work zone's crew of an incoming automated CMV that may not react to the work zone. As each vehicle arrived at the beginning of the restricted lane use zone, it changed lanes. The passenger vehicle moved from the rightmost lane, which is closed at the work zone, to the middle lane, which is the lane directly adjacent to the work zone. The trucks moved over to the leftmost lane, providing an additional 1-lane buffer to minimize close interaction with the construction workers. As each vehicle arrived at the end of the work zone, it returned to its original lane, the rightmost lane. After reaching the end of the reduced speed zone, the vehicles increased their speeds to the original travel speed of the highway. The Workzone use case demonstration allowed researchers to successfully demonstrate the capabilities for an automated truck to safely pass through a work zone, furthering the goal to improve the overall safety of all our nation's work zones. Through communication and automation of trucks at work zones, compliance to traffic rules will be improved and lives will be saved.